Hey everyone! So, today we're going to tackle a topic that I know sounds a little intimidating, dynamic programming. But trust me, it's actually one of the most powerful and honestly kind of elegant techniques you can have in your toolkit. So, you ready to dive in? You ever get that feeling that you're just solving the same problem over and over again? Maybe in your code, or even just in real life, right? Like, you figure out the best way to get to class, and then 5 minutes later, your friend asks, and you have to figure it all out again. It's just this feeling of wasted effort, and that is exactly what we're going to tackle today. Okay, so before we jump into the really smart way of doing things, we first have to talk about the hard way. This is where most of us start, and it really shows you why a solution like dynamic programming even exists. So let's talk about a technique called recursion. It's a really natural and sometimes even beautiful way to solve big problems. The idea is you just break them down into smaller and smaller pieces. I always think of it like those Russian nesting dolls. To figure out the big doll, you open it up to see the smaller one inside, and you keep doing that until you get to the tiniest, simplest one. Make sense, right? But, and there's always a but, here's the catch. As elegant as recursion can be, if you're not careful, it can be super wasteful. And that's because it has no memory. It will happily calculate the same thing over and over and over again without ever stopping to think, hey, wait a minute, haven't I done this before? Okay, check this out. This is a recursion tree for a matrix chain multiplication problem. Just look at it for a second. See anything repetitive? Look, the calculation from matrix chain 3, 4 shows up here, and then way over here again in a totally different branch. That's a huge waste of effort, a waste of CPU cycles. And believe me, this problem gets exponentially worse as the main problem gets bigger. So the big question is, how do we fix this mess? Well, we work smarter, not harder. And that brings us to dynamic programming, or what I love to call the lazy genius method. It is all about being efficient, but in a really, really clever way. And really, the whole idea boils down to this one simple question. This is the aha moment. What if we just write down the answer so we don't have to calculate it again? It's that simple. It's like when you solve a really tough math problem and you jot the answer down in the margin of your notebook, just in case. Why would you solve it all over again if you can just remember it? And that's the essence of it. You can think of dynamic programming as just recursion, but with a memory. You're still breaking the big problem down into smaller ones. But, and this is the crucial part, every time you solve one of those little subproblems, you store the result. You save it somewhere. That way, the next time you see that exact same subproblem, you don't recalculate. You just look up the answer. Simple as that. And this comparison here just makes it crystal clear. With plain old recursion, you're recomputing answers, which, as we saw, can be painfully slow. But with dynamic programming, you're storing the answers. This makes it so much faster. It takes that wasteful process and turns it into something incredibly efficient. It is, like I said, the absolute definition of being productively lazy. Okay, so you can't just throw dynamic programming at every problem and expect it to work. Nope. The problem itself has to have a certain kind of structure. It needs what I like to call the secret sauce, which is basically made of two key ingredients. So first up, you need what we call overlapping subproblems. This is exactly what we saw in that matrix chain tree. You're solving the same small problems over and over. I mean, if you're not, then there's no point in remembering the answers, right? And second, you need something called optimal substructure. That's a fancy way of saying that the best solution to the big problem can be built up from the best solutions of its smaller parts.
All right, theory is great and all, but let's make this real. We're going to walk through a classic example, and I'm telling you, you will absolutely see this on an exam. It's called the 0-1 knapsack problem, and it's the perfect way to see dynamic programming in action.
Okay, I want you to imagine something. You're a burglar, but you're a very logical, organized burglar. You've got a knapsack, but it can only hold so much weight. In front of you, there's a bunch of items. Each one has a weight, and each one has a profit value. For every single item, you have a simple choice. You either take it, that's the 1, or you leave it, that's the 0. And you can't take like half an item. Your goal, maximize the total profit of whatever you can fit in your bag. Now, to solve this, using dynamic programming, we need a little formula. A piece of logic that's going to make the decision for us at every single step. This is what we call the recurrence relation. Now, don't let the name scare you. Just think of it as the brain of our solution. It's the logic engine that drives everything. I know this formula looks a little intense at first glance, but let's break it down. All it's doing is asking a really simple question for each and every item. The question is it better for me to leave this item behind or is it better for me to take it? Option 1 is the profit we already have without this new item. Option 2 is the profit of this new item plus whatever the best profit we could get with the leftover space in our bag. And we pick the max. We pick whichever one is bigger. That's it. So let's see how this actually plays out. We start with nothing. Set as 0, 0 items means 0 profit and 0 weight. Easy. Then we look at the first item. We can either leave it or we can take it, which gives us a profit of 1 and a weight of 2. For the next step, as 2, we consider the second item and build on all the possibilities from the last step. You see what's happening? We're building up the best possible answer, one step at a time. And when we get to the very end, our final set, S3, we just have to look for the pair with the biggest profit. And there it is, the pair 6, 6. That tells us our answer. The maximum profit we can get is 6, for a total weight of 6. We did it. We found the optimal solution, not by guessing, but by carefully building it up from the bottom. Okay, everybody, pens out. This next part is basically your exam cheat sheet. If you're studying for your finals, this is the high-level summary you need to lock into your brain. So let's recap the key concepts. Number 1, what's the goal? To avoid recomputing stuff. Simple. Number 2, what are the 2 conditions you need? You need overlapping subproblems and optimal substructure. And finally, what are the 2 main strategies? There's tabulation, which is the bottom-up way we just did with the knapsack problem where you fill out a table, and then there's memoization, which is more of a top-down recursive way that just remembers or caches its results as it goes along. So, when you're out there and you face a tough problem, here is your 4-step plan. Step 1, just ask yourself, hey, does this look like a DP problem? Check for those 2 conditions. Step 2, figure out the brain of the solution, that recurrence relation. Step 3, choose your weapon. Are you going to go with memoization or tabulation? And finally, step 4, code it up and solve the thing.
So, I'm going to leave you with a question to think about. Now that you know the trick, this secret behind dynamic programming, where else could you use it? Because this isn't just for coding interviews, you know? It's a way of thinking. Think about planning a big project, or maybe your workout routine, or even a trip. Where in your life are you repeating work? And how could you maybe store a result to make your next decision just a little bit easier? Something to think about. Thanks for tuning in.